Okay, let's continue with the disk method, and a sort of a subset of the disk method, if you will, is something called the washer method. I'm going to illustrate it with this example right here, number 3. So we've got the region bounded between y equal x. Okay, so y equal x is just the line of slope 1, right, passing through the origin, 0, 0, 1, 1. Those are points on the curve, so I'll just draw that line. I'm going to stick it to just the first quadrant, though, remember. And then y equals x squared. That's the parabola opening upward. 0 squared is 0, 1 squared is 1. But you know how that graph looks, right? It's coming up this way. Okay, so the only bounded region we have is this region right here, right, between these two curves. And so what we're going to do is rotate this about the x-axis. So here is the x-axis here, or sometimes called y equals 0, right? So we're going to rotate about that axis. And what shape are we going to get? Well, I had a student that did a 3D model to help illustrate this, and let's see if we can see what this is going to look like. This cross-sectional area you can see is right here, okay? But we're going to rotate that region about the x-axis, and as we do, it's sort of a cutout of this funnel shape we get, okay? All right, on the outside it looks kind of like a cone. Looks like a cone from you know, after this rotates around, looking at it from, you know, this side over here, from the negative x-axis, if you will, right? We're going to get this cone shape. But if we look at it this way, right, we're going to see this. Of course, it would be filled all the way in. This is sort of like a cutout version, so you can actually see that cross-sectional area there. That's rotating again about the x-axis. So as we rotate that thing about, right, this is the shape we're getting. Okay. Anyway, I think that was kind of neat. So that is the volume of our object. So, or we're trying to find the volume of the of this object. What, you know, the capacity inside, right? So what the amount of material that I used to make this 3D model, let's say, if it were to go all the way around. So what will that be? So again, I'm going about a horizontal axis, and so again we're going to integrate with respect to x, and you see clearly we're going from x equals 0 to x equal 1, right? That's where this region is bounded on the x-axis. And if I pick an arbitrary interval here and take a look at it, then I've got a rectangle that I want to rotate for this segment about the x-axis. So what do we get there? Well, in this case, this outer edge comes around and forms obviously a circle. But this bottom edge of the rectangle goes around and forms a circle as well, which creates a hole in our disk, right? And we have a hole. This is our normal disk. We have a hole in the disk, and right there in the center of this, of both of these circles, right, that coming out here, that's the x-axis, right? Okay, it's y equals 0, and the area we're looking for then is this, right? And we call this a washer. I don't know if you know what a washer is, but right, we use them when we're dealing with bolts and things like that to tighten things up. Washers are helpful for that. So this is a washer. It's just really the disk method, you know, with a hole in it, but we call it a washer. And so there's two radiuses this time. We have our normal radius to the outer edge, right, which I'll use capital R like we've done before, and then we have the radius of the smaller circle. I'll call that little r. So what is the cross-sectional area here? Well, it's the big circle, which is what, pi r squared, minus the little circle, which is pi little r squared. And if we want to, we can factor that pi out, and we get this, right? And that's the idea behind what we have set up here, the so-called washer method. And remember, we have an outer and an inner radius. For the outer is for the bigger circle, the inner radius is for the hole in the middle, the smaller circle there. And you can see the capital R squared minus little r squared, the pi comes out integrating from a to b. So it's just basically one, taking one disk and then subtracting the smaller disk from it to get the result. So the goal is to then find the values of the big R and the little r. So let's see what those would be. So the big R is from what, the x-axis to the top of our rectangle in this case. So right here, this distance here is big R. And so what is big R? Well, its top is on, right, the top of the rectangle is on this line, which is y equal x, right? So the y value, the height, is x minus what? Y equals 0. So x minus 0 is just x, right? That's this height x. As we go from 0 to 1, this height is x. But then what's the little r? Little r is from the x-axis again to the what? The bottom, right? It's just this distance here. That right there. That's the little r. Just that little distance there. Well, that's obviously from y equals 0 to what? The bottom of this curve, which is what? Y equal x squared. And so little r is equal to x squared. And on the interval from 0 to 1, that makes sense, because on the interval from 0 to 1, the value of x is greater than the value of x squared. Think about a half, right? A half versus 1/2 squared is 1/4, right? X is bigger than x squared for that, and that's reflective in this graph. Okay, so now we have all the pieces we're ready to integrate, right, to find the volume. The volume is, and we'll pull this pi out. And what are we integrating with respect to? Again, x, right? X varies from 0 to 1. And we have capital R, which is x squared, minus little r, which is x squared squared. And there is our integral. Of course, x squared squared is x to the 4th. Okay. And we can now evaluate this fairly easily. Pi comes out here. Antiderivative of x squared is 1/3 x cubed. X to the 4th is 1/5 x to the 5th. And then evaluate it at 1, we get 1/3 minus 1/5. At 0, we get 0. So minus 0, we get this. And 1/3 minus 1/5, 1/3 is common denominator here is 15, right? So this is 5/15 if I multiply top and bottom by 5, and this is multiply top and bottom by 3, 3/15. So what is 5/15 minus 3/15? That's 2/15. So 2 pi over 15. Okay, well, let's do some setups. We've been doing examples where we rotated either about the x-axis or y-axis, but there are other vertical or horizontal lines that we can rotate about, and we use the same technique. We just need to find out, do we have a disk, do we have a washer, and then what are the radiuses for those, the big circle and the middle circle, the smaller circle. In a sense, you can say this is the washer method is, an extension on the disk method. The disk method is just where little r is equal to 0. If little r is equal to 0, we're right back to where we were with the disk method. So if little r goes to 0, if that inner circle goes to 0, if there's no washer, then it's the disk method. All right, let's take a look at some examples. We're going to set up these, but we're not going to evaluate the integral. You can, evaluate the integral if you want to. We're just going to set up the integral and then not evaluate it. And we're going to, in each case, be looking at the region bounded by y equal to the square root of x. y equals 0 and x equal 4. Well, here's y equal the square root of x right here. Right? Y equals 0, again, we know is the x-axis. Right? And then x equal 4 is this vertical line right here. And so you see the region here, we'll slightly shade that in. That's the region we're talking about. And we're going to rotate this again about the x-axis. Okay, and then we'll do some other lines in the next two examples. But here, we're going to take the same region and rotate it about different axes. So here it is about the x-axis. So again, we're going to integrate with respect to x because it's a horizontal axis. And our arbitrary rectangle we'll draw right here. Rotate that about. We get a disk. And there's no washer, right? There's no inner opening because this right here is the x-axis, again, coming out the center of our circle. And so the radius is indeed just from the x-axis to the top. That's our capital R. The area, therefore, is pi r squared. And what is r equal to? Well, the height of this curve is given by this function, so we note that r is equal to just the square root of x. And so we can set up our volume now. The volume is integrating. Where are we integrating from? Where does this region cover on the x-axis? From 0 to what? To 4, right? Integrating from 0 to 4, pi r squared. And r in this case is the square root of x. And we can clean this up a little bit. I can pull the pi out. 0 to 4. Square root of x squared is just x dx. And there's the setup. I mean, you can evaluate that, but that's the integral needed to find the volume. Pretty easy integral to evaluate. You can quickly do that. Okay. Now, let's change it around. This same region, we're going to now rotate not about the x-axis, but about the line y equal -2. So the region again is the same. All right, so here's the square root of x again. Here's, so just to remind you, this is y equal the square root of x. Here's x equal 4, y equals 0. So here's the region. But this time, we're going to rotate about the line y equal -2. So that's a horizontal line down here. This is the line y equal -2 there. We're going to rotate about this. Okay. So what kind of shape are we going to get? This piece is going to come out and then go back in down here somewhere. Let's sort of just mirror that down here, what it's going to look like. Okay. And, you know, we've got these circles here. And we've got okay. Anyway, what do we have then is there's a cylinder through the middle of this solid, and if I were to take this and sort of set it like this could be maybe something like a stand to put a you know, flagpole in or something. You take the pole and you stick it down here right into the cylinder, and it's got, you know, stuff all around it, so to speak, right? And we're trying to find the volume now of the region, right? So really this cylinder is not, inside of it is not part of the volume. We're looking for the volume of this exterior piece, right? This sort of stand, if you will, for a pole or for a flag or something like that. But again, you know, we're going to integrate with respect to x because it's a horizontal axis. But now here's our arbitrary rectangle. Okay. Now when I rotate this about, it comes back into the page down here, right? So it comes out and comes back in. So what are we going to have? Not a disk, but a washer. right? We got a washer. Okay, and right in the middle of that, what is the axis? Where are we coming out of here? What is this? It's right here. This is y equal -2, right? That's what we're rotating about. And so we have, remember, the smaller circle we'll call little r, and the bigger circle we'll call big R. All right? And so we know, again, the area is pi, what? Big R squared minus little r squared. So we got to find expressions for big R and little r. So let's look at big R first of all. Big R comes from y equal -2, what? To the top of our rectangle here. So from here all the way there, this is R. And so the top is what? Y equals square root of x. What's the bottom? Y equal -2. What's the difference? The square root of x minus a -2 is the square root of x plus 2. And that's what capital R is, the square root of x plus 2. You can realize our rectangle, its height is the square root of x, and then we're adding how much? This distance is always the same, right? It's always 2 units from the x-axis to y equal -2. So it's the square root of x plus 2, always. And we can see our formula works because our radius, when x is 0, is just 1, right? This circle right here, x is 1. And when x is 0, we get, radius is 2. 2 units, right? That's -2. X equals 0 down to -2 is 2 units. So when I plug in x is 0, I get 2. And then at the extreme end, right, our radius is now what? Here is our circle, and our radius is 4, isn't it? From 2 all the way down to -2, it's 4. And you can see that when x is 4, square root of 4 is 2. 2 plus 2, we get 4, which is the radius. So it's working. Little r, what's little r? Little r is going to be, again, from y equal -2, but this time to the bottom, right? It's going to be this distance here. What do you recognize about that distance? It's always equal to what? 2 units, right? Because it's from y equals 0 down to y equal -2. So 0 minus a -2, our little r is equal to 2. Okay. Bottom line is you can always do, the top minus the bottom to get, the values of the radiuses that you're interested in. And so that little r radius always is the same. So that's this circle in the middle here, this hole, right, stays the same all the way throughout. The outer ring, right, gets bigger or smaller depending upon how x varies. From 0 it's small and goes up to a radius of 2 at x equal 4. All right, so now we're ready to set up the integral. The volume is pi. Pull that pi out. Integral from where to where? What are we integrating? Same thing, from x equals 0 to x equal 4, because that's where our region is, right? Still the same region that we had before, from 0 to 4. And it's big R squared. Square root of x plus 2 is big R squared, so notice that has to be quantity squared, minus little r squared, which is 2 squared. All right, and we could say 2 squared, I guess, is 4, but there it is. That's the setup integral. And you don't have to go through, I guess you could FOIL this out, but just leave it like this. If it's just a setup, this is good enough that you get it set up. You don't have to evaluate it. You can evaluate it if you want to, but on a test, time-wise, I would just go ahead and set up the integral. The last one is I want to take the same region here and rotate about the line y equal 2. So remember, we're doing x equal 4. We've got y equals 0 there, so this is our region. And now we're going to rotate it about the line y equal positive 2. So y equal positive 2 is right here. And now we're going to rotate it about this axis. And this region is going to come up and go back in so that it's going to look something like this. Going back into the right. rotate around, go back in, and rotate around. From the outside, if we look on the outside, it looks like a perfect cylinder. But if I look from this way, I see this sort of funnel shape cut, into that cylinder. So we're looking for the volume, not just of the cylinder, the whole cylinder, but cylinder minus this funnel shape region, basically. So how do we proceed? Again, we take an arbitrary rectangle here, just like we've been doing. But notice this time we're going to rotate it up and about here, right? So it's going to go into, that rectangle will go into, back into the page, if you will, up here, and then continue to circle around, right? Again, we're going to get a washer, aren't we? Going to get a washer. And again, the center of both of these circles is y equal 2 this time, right? Y equal 2. But notice this, when we look at our inner radius, we'll call that little r, and our outer radius, we'll call that big R. Notice the inner radius, we're going to come, where do we start from? From y equal 2. And so notice the top of the rectangle now, from y equal 2 to the top of that rectangle, that's little r. Right, that's little r, right? So that's the hole in our, and notice is we got to, basically the whole encompasses the whole thing, right, at x equals 0. But as x gets closer and closer to 4, that whole radius is getting smaller, 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 isn't it, going to 0. In fact, what is this little r? Well, the top of it is where? The top is at what? Y equal 2. But where's the bottom? Minus what? The bottom is at this curve, which is what? Again, this is y equal the square root of x. Forget that y equal the square root of x. This was the, so it's the square root of 2, or sorry, 2 minus the square root of x. And notice that works when x is 0. When x is 0, what do I get? 2 minus square root of 0, 2 minus 0. I get 2. That is indeed the radius. Notice this, the circular region down here, the radius is 2. By the time we get, as x gets closer and closer to 4, that radius is approaching 0. And if I plug in x equal 4, 2 minus the square root of 4 is 2 minus 2 is 0. Capital R, what's capital R? Well, that again is from y equal 2, this time to the bottom of our rectangle, from y equal 2 to the bottom, right? That's big R. Right, and because this outer, this bottom of the rectangle is going to flip around and go back into the page, circling around, that's going to form the outer edge of this ring. Okay, and so what is that? Well, from y equal 2 to y equal what? This is the x-axis. Y equals 0. 2 minus 0 is 2. And notice that's the case, right? This edge right here forms the outer edge of this outer circle, right, each time, and we're getting a fixed radius there. So we can set this up. The volume is, again, we're integrating what? From 0 to 4. Big R is 2 squared minus little r is 2 minus the square root of x squared, and that's our integral setup. Of course, 2 squared we can say is 4, but that's the integral we need to find the volume of this solid. Okay, so these are a little tricky to set up, but you'll need to practice a lot of examples, and we'll continue this discussion in the next set of next video or so. We're going to talk about a method called the shell method, and then sort of see how these two methods can be used and what are the benefits of the disk method versus this so-called shell method that we'll look at next.